Hello, physicists, and welcome. We'll be covering momentum 2 in this session. Our learning objectives are: I can calculate the change of momentum of an object, delta P is equal to delta mv, and I know impulse, J equals F times T, on an object changes the object's motion. Let's get started. Let's take care of some bookkeeping first. Okay. Hey, we're looking at the change of momentum and in the calculation. In math and in physics, the change symbol is the Greek letter delta. And we're looking at a change in momentum, so we have delta P, P being our symbol for momentum. Remember that P, momentum, is equal to the value of mass times velocity. If we want to be fancy, we know that both velocity and momentum are vectors, that are quantities with direction. So if our momentum is mass times velocity, our change of momentum is the change of momentum is equal to the change of the quantity mass times velocity. The change in momentum can be due to a change in mass, a change in velocity, which is what we'll be doing most of the time, or it could be a change of both. Okay, so just another way of expressing this is our change of momentum can be equal to our change of mass times a velocity. Our change of momentum can be mass times a change of velocity. And a reminder that v is a vector. So our delta v is also a vector. That also means that p is a vector and delta p is a vector. Let's go through some sample calculations. Hey, the first one, we have a car. We're going to assume it's initially stopped, so our initial velocity is equal to 0, and it's going to speed up to, and let's say a speed of our final velocity is going to be a speed of, let's say, 20 meters per second, and the mass of our car is equal to 800 kilograms. I had no change in my mass, so my change in momentum is going to be equal to mass times my change in velocity. Change in velocity is going to be equal to our final velocity minus our initial velocity. Let's go put the numbers in. So our mass, 800 kilograms. Our final velocity, 20 meters per second, minus 0 meters per second, is 20 meters per second. Our change in momentum is, let's see, 16,000 kilogram meters per second. And because this is a positive value, it has more momentum to the right at the end of this time interval. Let's take a look at another example. Hey, we have an airplane landing on a carrier deck. Let's see, a couple of notes. Hey, when it's initially getting to the carrier, it does have a velocity to the right. And a good estimate of that would be about 70 meters per second. After it stops on the deck, our final velocity will, of course, be 0 meters per second. A mass of a aircraft like this, a good estimate be about 4,000 kilograms. Our change in momentum, again, is going to be our mass times our change in velocity. Our change in velocity is our final velocity minus our initial velocity. So watch in this case. Our final velocity is going to be 0. Our initial velocity is 70 meters per second. So how much did our velocity change by? Minus 70 meters per second. Let's go ahead and put our numbers in here. Our change in momentum is the 4,000 kilograms times minus 70 meters per second. I'll have to write it on the airplane here. So our change in momentum is minus 28. Oops, is that right? Let me just make 7 times 20. Whoops, I got to go another 0 there. Minus 280,000 kilogram meters per second. We could say that it's slowing down, or the change in momentum is to the left. Not all change of momentum involves objects that start or stop. Let's take a look at this. Hey, initially I have a soccer ball, and the mass of the soccer ball is about 0.4 kilograms. Initially it's rolling to the right, hits the wall, bounces off, and then starts rolling back to the left. Let's go and figure out what this value is. Again, our change of momentum is going to be equal to no change in mass. So mass times our change in velocity. Let's take a look at our initial velocity is going to be equal to 10 meters per second to the right? Hey, our final velocity is going to be equal to, this is to the left, minus 8 meters per second. Let's go with our change of, so our change in momentum, let's go with our change of velocity. Our change of velocity is going to be our final velocity minus 8 meters per second minus our initial velocity, 10 meters per second. What does that mean? Our velocity changed minus 18 meters per second. The difference between a positive 10 and a minus 8 is negative 18. Let's put it all together. Our change of momentum is going to be equal to our mass times our change in velocity, in this case 0.4 kilograms, times minus 18 meters per second. What's our change of momentum? That is a minus 7.2 kilogram meters per second. Why is it minus? Because the change is to the left. Let's take a look at what it takes to change momentum. Hey, what does it take? It takes a force, and it needs to be applied for a certain time interval. Okay. And let's quickly define a force. At this point, we'll just define it as a push or a pull, and a force is something that causes a change of motion. But this value of force and time is referred to as an impulse. Okay. In fact, impulse, given the symbol A, is equal to the quantity of force times the quantity of time. Because that's required to change impulse, our impulse, force times time, is equal to our change of momentum. If we wanted to add one more line in here, is equal to our mass times velocity. We'll look at two examples of that. First is the game Jai Alai. The other is golf. This is the sport of Jai Alai, played on a court similar to a racquetball court, but rather than rackets, notice the long scoops the players have. It allows them to hold on to the ball much longer so they can have high velocities with reasonably low forces. Here we see a swing from Tiger Woods when he's about to strike a golf ball. Notice this is in slow motion, but notice as he starts his swing, he has a long time that he's swinging the club, allowing him to provide a lot of momentum to the club. But once he strikes the ball, the contact time between the club and the ball is very short, so the forces need to be very high to increase the velocity of the ball. So in both the game of Jai Alai and in golf, the final momentum of the ball is about the same. And in Jai Alai, that's achieved by having lower forces, but much longer times. In golf, the force during contact is very high, but the contact time is very low. But the product of each of these provides our impulse, which is the way that we change the momentum in the ball from standing still to moving very quickly. Let's wrap up. Hey, so for momentum section 2, can you now, let's review our learning objectives. Can you now calculate the change of momentum of an object? And do you now know that impulse, force times time on an object, changes the object's momentum? That's it for now.